All right, hi everybody. Today we're going to talk about calorimetry and heat transfer. This is the very last lecture that you'll have to listen to from me. But I want to tell you guys, I am just as upset about not being able to see you guys in person in the classroom as I'm sure you guys are, or maybe you're not, I don't know. But I know it's heartbreaking not knowing if you will have a graduation or not. But I enjoy going to graduation too and seeing you, and you know, you might be valedictorian or salutatorian and be giving speeches and things like that. And it's always good to hear about your future plans and to see everybody going on to something new. And so as much as you guys are upset about it, so are we as your teachers. We miss seeing you in class. This is not an ideal situation. I don't like doing lecture videos this way. And I wish I could see you guys in person. So just to throw this out, if you ever need anything chemistry-wise, biology-wise, when you're in college, in the future, whatever the case may be, do not hesitate to email me, come back and visit, whatever the case may be. All right. So everybody, if I don't see you, good luck. But hopefully we get to see each other again here before, you know, you go off to college. All right, with that being said, again, I hope you're all excited. This is the last lecture video that you're going to have to watch, if you've been watching them. But this video is about calorimetry, heat transfer, and it's going to take calorimetry worksheet and the heat transfer worksheet. It's the last two things you're going to have to do. On the calorimetry worksheet, so I'll already tell you this. This was kind of my bad. I thought these problems were more geared to calorimetry than they were. On the calorimetry worksheet, and of course I only had a week to get 6 weeks worth of work ready for all my classes, so that's why some of these worksheets weren't as great as others. The calorimetry worksheet, we're only going to do number 2. Okay, there's only 4 problems on that worksheet, but you can go ahead and get rid of numbers 1, 3, and 4. Go ahead and cross those out. Only have to do number 2. With the specific heat and heat transfer worksheet, we are going to be doing, and I'll write that on here, specific heat and heat transfer worksheet. You should have done those specific heat calculations, the calculating heats numbers 1 through 5. You probably should have done those already with the last lecture that we did on specific heat. So for calorimetry, for this calculation, you're going to be looking at numbers 7, and I don't know why number 6 is just a title, but number 7 through 16, okay, is what you're going to do on that one. And so you don't have a lot of problems here, 7 through 16, and then number 2 on that calorimetry worksheet, and that will take you to the end of this work. Yay! All right, so let's take a look at exactly what we're dealing with here. Calorimetry, what we're going to do is we're actually going to take a piece of metal, we're going to heat it up, okay, and then we're going to place it into water, okay, water that's usually at room temperature. And what the goal here is to see how much heat is transferred from the warm metal to the cold water. Okay, and so this is called a heat transfer, or calorimetry. And this is how we figure out actually how many calories are in something, okay, in terms of our food. We figure out how much heat energy is absorbed by the water in our bodies, basically, when we go to eat it. And that gives us kind of an idea of how many calories are in food. And obviously it's a little bit more specific than that, but that kind of gives you an overall idea of it. But what we're going to look at here is we're going to have an equation that looks like this. It's going to say that the negative Q, so the negative heat that is lost by the system, because when you lose heat, it's negative, is going to be equal to the positive heat that is gained by the system. Okay, because we're transferring heat. And so what's lost from one thing is gained from the other. Keep in mind that energy cannot be created or destroyed. It can only be transferred, okay, from one type to another. So in this particular case, if we lose energy in one piece or one metal, we're going to gain it, okay, in the water. And so we can also write this as the negative Q of the metal, which I prefer, is equal to the Q of the water. okay, the heat that is gained by the water. And that'll kind of help you work through some of these problems, okay? And so remember, this is another thing you're going to need to know. Remember, Q is equal to mc delta T. That's the mass times the specific heat capacity constant times your delta T, your change in your temperature in Celsius degrees. So even another way to write this is that the negative mass of the metal times the specific heat of the metal times the temperature change of the metal, okay, and this is all negative, is going to be equal to the mass times specific heat times temperature change of the water, okay? And so when we work out these problems, that'll kind of give you a little bit of guidance as to how to do this. And so what I'm going to do is I'm going to go ahead and jump into a problem, and I think that will help you to figure this out. I'm going to try and leave that right there so we can see it. So let's take a look at that calorimetry worksheet. Remember, you only have to do number 2, so that's the one we're going to focus on as kind of our sample problem here. For number 2, it says a 75-gram sample of metal is placed in boiling water until its temperature is 100 degrees Celsius. A calorimeter that contains 100 grams of water, which temperature is 24.4 degrees Celsius. The metal sample is removed from its boiling water, immediately placed in the water from the calorimeter. The final temperature of the metal and water in the calorimeter is 34.9 degrees Celsius. Assuming that the calorimeter provides perfect insulation, what is the specific heat capacity of the metal? The specific heat of water, as always, is 4.184 joules per gram degree Celsius. Now, that's a lot of information. But here's what I want you to do whenever you start these problems. I want you to group these things into metal and water. Those are the 2 categories that we need to group things into. And I want you to write down what we need to know about each. We need to know or find the mass, the specific heat capacity, and the temperature change of the metal. And that is all going to equal the mass, the temperature, or the specific heat capacity, and the temperature change in the water, okay, just like we have up here. So we had to figure out what in this problem applies to each one of those different variables, okay. So it says a 75-gram sample of metal. All right, so there we go, 75-gram sample, that's our mass, okay. It is placed into boiling water until its temperature is 100 degrees Celsius, okay. So our initial temperature, I'm going to write IT. Our initial temperature of our metal is 100 degrees Celsius. Okay. A calorimeter contains 100 grams of water. Okay, mass of water, 100 grams. Its temperature to start out with, and so I'm going to write IT, initial temperature, was 24.4 degrees Celsius. The metal sample is removed from the boiling water. It's immediately placed in the water in the calorimeter, and the final temperature of the metal and the water is 34.9 degrees Celsius. So final temperature, 34.9 degrees Celsius. And keep in mind, because we add the metal to the water and we let it set, whatever the final temperature of the water is the same as the final temperature of the metal. So if it would only give you, oh, the final temperature of the water is 34.9, well, the metal's in there. And so that also has to be the same as the temperature of the metal. So my final temperature is 34.9 degrees Celsius. Okay, it says, okay, and so it says also that the specific heat of water is 4.184, and that's joules per gram degree Celsius. And it says, what is the specific heat of the metal? So in this problem, we will be calculating C. Okay, delta T, remember, is final minus initial. 34.9 is our final minus 100. Now, notice you're going to end up with a negative temperature change. Again, whenever you do this problem up here, it has a negative sign in front of that Q for the metal. When we multiply our negative sign by our negative temperature change, it will become positive. So your C value will end up as a positive. Okay, so do keep that in mind, and I'll show you that as we work the problem. Final temperature here, 34.9, minus your initial, 24.4. Okay, and so that is going to give you your temperature change there. I'm not going to do the temperature change. I'm just going to work it into my problem and show you how that goes. All right, and so we're going to use the equation negative mass times C times delta T, okay, and this is our metal over here, is equal to the positive mass times C times delta T over here, and that is of the water. And we're going to plug and chug at this point. So a negative 75 grams, okay, times our C value, which we don't know what that is, that's what we're trying to find, times our change in temperature, 34.9 minus 100, is equal to the mass of the water, 100 grams, times 4.184, times 34.9 minus 24.4. Okay? Now, this is simple math over here, so I'm going to go ahead and multiply over on the right. And when I do all that multiplication, I do everything that I need to, I get a number of 4,393.2. Over here on this side, okay, I'm going to go ahead and take my negative. I'm going to multiply a negative 75 grams times my temperature change here. And when I do that, I get a positive value, okay, and I get a positive 4882.5. And I still have my specific heat capacity variable. To solve for C, I need to get it by itself, so I divide both sides by 4882.5. And when I do that, it gives me my specific heat of my metal. And my specific heat of my metal is 9 joules per gram degree Celsius. Okay? That's what you're doing. Guys, if we were in school, I would ask you to do a lab where we actually took different types of metals, like aluminum, lead, iron, copper. We would actually heat them up in boiling water, let them set in boiling water for a certain amount of time so they got to a temperature of 100 degrees Celsius. We would take them out of that beaker, put them into room temperature water in a calorimeter, and we would let them sit until the water reaches a certain temperature. And then I would have you calculate, just like we did here, the specific heat capacity of the metal, okay, and see how close you were to the actual specific heat capacity that we know. All right, so this would have been a lab activity that we could have done, and you could have seen how it worked actually firsthand. All right, so that was number 2. Remember, you don't have to do problems numbers 1, 3, and 4. So let's go ahead and move on to the specific heat and heat transfer worksheet. We're going to go ahead and take a look at number 7. I'm going to do numbers 7, 8, and 11 for you. 7 and 8 are just like what we did. Number 11 asks you to find the mass. And then all of the rest of them are just like the problem we just did. And so I'm going to let you guys kind of take over on that when we get to that point. All right, so let's take a look at number 7 from this worksheet. Number 7 says, an alloy of an unknown composition is heated to 137 degrees Celsius. It's placed into 100 grams of water at 25 degrees Celsius. If the final temperature of the water is 36.4 degrees Celsius and the alloy weighed 2.71 grams, what is the specific heat capacity of the alloy? All right, as always, the first thing I like to do is I like to separate everything into metal and water so I can easily figure out my variables. My mass, my specific heat, my temperature change. Mass, specific heat, temperature change. Specific heat of water, always the same, 4.184, so I can go ahead and write that one down. The alloy is heated to 137 degrees, placed into 100 grams of water. Go ahead and do 100 grams of water. Okay. And I can say the alloy was originally 2.71 grams. We are trying to find the specific heat capacity of the alloy, so we're trying to find the C. And so to figure out which one was my final and my initial, remember the final temperature of the metal is the same as the final temperature of the water. So here it just says the final temperature of the water. Final temperature of the water is 36.4 degrees Celsius. The initial temperature, it was originally heated to 137 degrees Celsius. That was my initial. Again, you should get a negative number there for your metal. Temperature change for the water. Again, we know the final is the same as the final for the metal, 36.4. The water was originally at 25 degrees Celsius, just about room temperature. Okay, that is a minus sign. It's a horribly long minus sign, but you know, there you go. All right, plug and chug. So I'm going to plug this in. The negative 2.71 grams of mass, times my C, which I don't know, times my temperature change, which I actually already calculated is a negative 100.6, okay, is going to be equal to the positive mass of the water times its specific heat capacity times the temperature change over here, which is a positive 11.4 degrees Celsius. Okay, I do my math, and on this side I end up with a 4769.76. Over here I end up with C, still by itself, times 272.626. To get C by itself, divide both sides by 272.626. And when I do that, I end up with a C value that is equal to 17.5, and that's joules per gram degrees Celsius. So that's actually a very high specific heat. Okay, very, very high. That's okay. It's okay. It's a very small amount of metal, which is then why it was a very high specific heat. Okay. All right, so that's number 7. I'm going to show you one more type of problem that's the same, just so that we have another practice. And then I'm going to show you one that actually wants you to calculate mass. And then I'm going to let you go on your own. All right, so number 8, if a 45-gram rock, and this time I know a rock isn't metal, but we're going to assume that the rock is the same as what the metal would be in most of these problems, is heated to 97.2 degrees Celsius, placed into 75.3 grams of water, which is originally at 32 degrees Celsius. The final temperature of the water was 46.2 degrees Celsius. What is the specific heat capacity of the rock? Always start out the same. Metal, water. MC delta T, MC delta T. The mass of the rock was 45 grams. We don't know what the specific heat was. That's what we're trying to find. Temperature, final temperature was 97.2. Or excuse me, initial temperature was 97.2. Final temperature of the rock and the water was 46.2. So 46.2 degrees Celsius minus the initial 97.2. Okay, the mass of the water was 75.3 grams. The C value always the same, 4.184 for water. And the temperature change, we went from a final temperature of 46.2 from our initial temperature of 32 degrees Celsius. Okay, plug and chug. Negative 45 grams times C times our temperature change, which is a negative 51 degrees Celsius, is equal to our positive 75.3 grams times our heat capacity for water, 4.184, okay, times our temperature change, which is a positive 14.2. Okay, when I do the math on this side, I get 4,473.78. Over here, I get C times 2295. Divide both sides by 2,295. Cancels it out over here. And our specific heat capacity for this particular rock is somewhere around 1.95 joules per gram degrees Celsius. Okay, now, since we have a good grasp on these problems, numbers 9, 10, 12 through 16 are all completed this same way. You are going to be solving for the specific heat capacity of the metal. Okay, so plug and chug, exact same way we've been doing here. Last one I'm going to do for you is number 11. It's not any harder. You're just solving for mass instead of specific heat capacity here. So again, I'm going to separate before I even read the problem, metal and water. Write down my things I need to know for both of those. I always know water is 4.184. And so I'm going to say a piece of copper has a temperature of 73.6 degrees Celsius. The metal is placed in 96.2 grams of water at 17.1 degrees Celsius. The temperature rises by 5.1. What is the mass of the metal? So the mass of the metal is what we're looking for. Specific heat capacity of copper, it says, is 0.377 joules per gram degrees Celsius. The mass of the water, it told me, was 96.2 grams. And the temperature change is a little bit different than normal. It says that when the metal is placed in the water the temperature rises by 5.1 degrees Celsius. So the temperature change of the water is going to be 5.1 degrees Celsius. We know that, okay? But we have to figure out the temperature change also of the metal. And so understanding that our initial temperature, so our initial temperature of the water was 17.1, and it rose by 5.1. We have to add that together to get our final temperature. And so our final temperature is actually 22.2 degrees Celsius. That's important because we need it for over here at our temperature change. And so again, we're going to use that as our final temperature for our metal as well. And we're going to subtract our initial temperature, our 73.6 degrees Celsius. Okay, it becomes a simple plug and chug again as well. So I'm going to come over here and I'm going to say my negative, I don't know what the mass is, times my C value now that I know, times my change in temperature, which ends up being a negative 51.4, is equal to my positive mass of my water times my specific heat capacity of water times the temperature change, which was 5.1. I do the math on this. Okay, I get 2052.8. Over here, I get a mass times 19.38. When I take this negative and multiply it, it becomes positive, so do keep that in mind. Divide both sides to get m by itself. Divide 19.38, and it ends up that my mass of my copper is 105.9 grams of copper. Okay. All right, guys, that's it. Okay, complete the rest of those problems, and they will begin collecting the packets, I assume, sometime after the week of May 8th. I think they're saying the week of May 18th is going to be packet collection. I think you have the week of the 8th through the 18th extra time to complete this, so please do so. But again, if you have any questions, always feel free to email me. Thanks, guys. Bye.